All right, guys. Hello again from me. We will continue our 302 lectures together. And what we will look at is that we will start what is called the state space representation. Okay? Representation. With those of you who were together with me, you would remember that we really started talking about state space representation very early, and I hope that other sections also have done the same with some examples on state space representation before a formal treatment. But now, for the rest of the term, we will actually spend some more quality time with this particular mathematical model, and we will see what kind of additional benefits that will give us. Remember that we basically have seen a number of mathematical representations. For example, we have seen essentially the differential equation representation. We have also seen transfer function representation. We have also seen some intermediate forms. For example, rather than having a single transfer function, we have also seen that we can use a block diagram representation, which is nothing but a transfer function representation, but with more details on the individual subsystems representation. Okay, so what we have also seen is that differential equation representation is basically a time domain way of describing system behavior, and the transfer function is in the Laplace domain. Laplace, or we can also say that it is in the frequency domain, because S is our complex frequency variable. Okay, and so is block diagram representation. So when we come back to the state space representation, we will see that state space representation in fact is also a time domain representation, which is similar to actually the differential equation representation, because the state space representation, what we have is we define something called the system states, okay, and we represent it with a vector x. Okay, so that is defined as a set of state variables where n is the system's order. Okay, so once we define these system states, what the state space representation does is that it expresses the derivative of these state variables as a linear combination of all the states and plus the inputs. Okay, so if we remember what in fact, we have done this to some extent, but let's remember that what we have is the derivative of the state variable, a matrix A times the vector of the state variables plus another matrix B times the vector of the inputs. Okay, so if X actually is a member of Rn, in that case, A is a member of the matrix space of n by n matrices. In that case, U, if it's a member of Rm, okay, so n is the system order or number of states equivalently. M in this case is the number of inputs to the system. So what happens is that in that case, the B matrix, in order to satisfy the properties of matrices, has to be an n by m matrix, okay? Because B has to be multiplied by an m by 1 vector in that case, okay? So U actually is a vector of inputs, okay? So we have U1 up to UM, okay? While X, so this is the definition of the input vector. And we also have the output of the system expressed as the multiplication of another matrix times the states. By the way, we can have multiple outputs as well as multiple inputs. That is one of the powers of the state space representation, because we know that, for example, transfer function representation is a single input, single output representation, but the state space representation can allow for multiple inputs and multiple outputs, okay? And also there can be a direct path from the input to the output, okay? So let me continue defining these variables. If my output is, let's say, of p variables, so where p is the number of outputs, in that case, C necessarily is a matrix between the states and the outputs. So it's going to be a matrix whose row order has to be equal to the output. So it's going to be P times N. Okay, and D has to be between the input and the output. So it has to be a member of R to the R P times M. Okay, so its row order is equal to P, which is the order of the output, and the column order has to be equal to M, which is the order of the input. Okay, so you see that in this representation, we have vectors and matrices. It is a time domain representation because when we have x dots, what we mean is that we have x1 dots, x2 dots, up to xn dots. And that is, by definition, equal to dx1 over dt up to dxn over dt. So in fact, we have a system of first order differential equations, okay? So state space representation is basically equivalent to a system of first order differential equations. So instead of having a single differential equation of order n, we now have n first order differential equations. So that's the difference from a simple differential equation representation. Okay, so let us come back to an example in order to clarify the representation. Okay, let us take a look at a familiar example, which is the RLC network. In fact, the series RLC network. Okay, so here's our example. We basically have an input. Let's call this U of t, the voltage, a voltage source, independent voltage source that derives a resistor, an inductor, and finally a capacitor in series. Okay, so we have R for the resistor, L for the inductor, and C for the capacitor. Now we know that because of the Kirchhoff's current law, basically a single current goes through this network, and this is also equal to the current through the inductor. And we obviously have voltages across the resistor, which is VR, voltage across the inductor, which we can call VL, and a voltage across the capacitor that is equal to VC. Now, I'm not going to go in detail again, citing Kirchhoff's current law, Kirchhoff's voltage law, how they are combined and so on. But let me show you where the derivatives of individual state variables comes from. Well, we know that for a capacitor, the terminal equation is C times dVc of t over dt is equal to IC of t, the current through the capacitor, right? So that is one of the equations. And if we take a look at the inductor, we have L times dIL of t over dt being equal to the voltage across the inductor, VL of t. Okay, so you see that when we are, in fact, this is a second order circuit. So if we were to combine everything into a single equation, we know that we would have a second order differential equation. Depending on which variable we choose to be our fundamental variable, that's going to be part of the differential equation. But if we take a look at the individual components and their terminal equations, in fact, naturally, we have first order differential equations. So instead of combining them into a second order differential equation, another way of doing it is to pick suitable states and try to write the equations as a system of first order differential equations. And if we do that and take a look at the terminal equations, the natural candidate for the states become apparent, okay? Because we have the derivatives of the capacitor voltage and the derivative of the inductor current, okay, VC and IL are the natural candidates of states. So I can define X1 state to be VC and X2 state as IL. And that's going to facilitate the rest of the construction of the state space system. Okay. Now let's take a look at how we can use these definitions to construct our state space representation. The only thing that I need to do is to express the derivative of each state as a linear combination of all the other states. So I will need to get rid of all the intermediate variables and try to write everything in terms of state variables. So let me try to do that, okay? Now let's take a look. X1 dot of t, the derivative of the first state, is nothing but dVc of t over dt. Now, from the capacitor equation, I know that this is equal to 1 over c times IC of t. Okay? Now, IC of t, unfortunately, is not one of the states. Okay? So I need to replace IC of t in terms of my states. And what are my states? My states are VC and IL. Now, from Kirchhoff's current law, I know that the same current flows through the circuit. So IC of t, in fact, is nothing but IL of t. So, which is one of my states. Okay? So, in that case, what I have is that I have this IL being the second state. So I have x1 dot of t equal to 1 over c times x2 of t. Okay? So that becomes one of our state equations. Now let's see whether we can construct a second state equation. Now here I have x2 dot of t, which is my second state equation, is equal to dIL of t over dt. And that is equal to 1 over L VL of t. Now VL of t again is not one of our state variables, so I will need to write down VL of t in terms of the other variables. What are those other variables? Well, I have the input, which I can use as part of my equation, and also I have IL and VC. So now I need to use the Kirchhoff's voltage law in order to express VL of t in terms of U of t and VC of t. Okay, so let us try to do that. We know that VL of t, so here's Kirchhoff's voltage law. Let's write it down over here. Okay, so I have minus minus U of t. I'm going to drop the time variable to simplify things a bit. Minus U plus VR plus VL plus VC is equal to 0. Okay, so I'm trying to write down VL of t. So let's write VL of t. VL of t is equal to U minus VR minus VC. Now VC is one of my state variables and U is my input, so I can keep those. But what about VR? VR is not one of my states, so I need to replace VR with one of my state variables. Now what is VR? VR is R times IR, but IR is equal to I and is equal to IL. So I can write for VR R times IL minus VC. So that is how I can express VL, which is not a state variable, in terms of state variables and the input. Okay, so let's write it down. So I will have U minus R times IL minus VC instead of VL. Okay. Oh, sorry about that. There is a problem here, over here, right? So I, instead of 1 over L, I just switched to 1 over C for whatever reason, I don't know. So let me just erase this part and correct that, okay? So that's gonna be 1 over L, okay? So, okay, so let's keep writing this. So this is going to be minus 1 over L times VC, and VC I know is my first state. Sorry, this is my 1, x1, minus R over L times IL, which is my second state, x2, and plus 1 over L times U, which is my input. And I can have an input term in my state equation. Okay. Now let us put these two equations in matrix form so that it starts resembling our state equations in the ABCD representation. Okay. So I have d over dt, the state vector, x1 and x2, is equal to a matrix A times my state variables x1 and x2 plus a vector which is B. Okay, so this is my A matrix, this is my B matrix. Now because I have here a single input U, okay, I will have a 2 by 1 matrix over here, and let's combine those from my equations. From the first equation, x1's derivative is equal to just 1 over c times x2. So 0 times x1, 1 over c times x2, and 0 times u comes from the first equation. And if we take a look at the second equation, well, I will have minus 1 over L times x1 minus R over L times x2 plus 1 over L times u. Okay? So we haven't defined the output of this system, but let's define y as, for example, Vc of t. This is the defined output, and we are free to define, obviously, whatever output that we want, depending on the problem. Now, what's going to be the output? It will be a 1 by 2 vector times the state variables, x1, x2. And how will we fill in this matrix? Well, because y is defined as the capacitor voltage, and that is nothing but our first state, so this is going to be a 1 and 0 multiplying the states plus 0 times u. Okay, so I don't have any direct connection between the input and the output. So we have reduced this into the form that we have defined. And in fact, this where I have x are vectors, u, y, everything are vectors, and I have matrices involved, okay? So I have reduced this into what is called the state space representation, or the ABCD representation. Okay, that is also sometimes utilized. Okay, so now we have a number of questions that we will need to address. Okay, one of the questions is what is the relationship between, for example, the transfer function representation and the state space representation. Okay, how can we go from one to another? Is that possible? Okay, now we will divide this into two. How can I obtain the transfer function from state space representation? Is it unique? Okay. That means, is there a one-to-one correspondence between the transfer function and the state space representation? Okay. Now, well, we will go in detail over this, but the short answer is that given a state space representation, there is a unique transfer function that we can obtain, but given a transfer function representation, unfortunately there are, or maybe fortunately, there are infinitely many transfer function representations for the same, state space representations for the same transfer function. Okay. Now let us first consider this. Okay, so the second question, this is for later, is how can I obtain a state space representation for a given transfer function representation? Again, is it unique? Okay, the answer is no, but we will come back to that in a minute. Okay, so let's take a look at the first question first. Now we will try to obtain the transfer function representation from the state space. So let's say that given, so let me put a title on that, okay? So let's say TF from SS, okay? So, so given our state space, given x dot is equal to ax plus bu, and y is equal to cx plus du, I have dropped the vector matrix notation for, or maybe I should put at least a vector notation for x. And but remember, in order to obtain a transfer function, we need to have single input and single output. Why? Well, because you know, the transfer function representation can only handle single input, single output systems, okay? While the state space representation is able to handle multiple inputs and multiple outputs. So if I want one transfer function, the state space representation should be a single input, single output system, so that I can obtain the transfer function, okay? Okay, so let's take a look at what we can do. Well, we know that the transfer function is in Laplace domain. So in order to and needs to assume also zero initial conditions. Okay, on top of being single input, single output. So assuming that, let's take the Laplace transform of the first equation. So I will have s times x of s equals a x of s plus b u of s. Okay. Now what I can do is that s times the identity matrix times x of s is equal to a times x of s plus b times u of s. Why do I put an identity matrix here, which does not change anything? But what I can do is that I can now take these into x of s parentheses. So I will have s times I minus a as a matrix expression times x of s is equal to b times u of s. Now, if Si minus A is invertible, we know that actually A is a square matrix, an n by n matrix, and Si minus A therefore is also a square matrix. So if this is invertible, what I can write is that I can express x of s as the inverse of Si minus A, a matrix inverse, times b times u of s. So what I was able to do is in the Laplace domain, I was able to express the states in terms of the inputs. This is in a sense the solution for the state variables, but we know that in order to have a time domain solution, obviously we need to take the inverse Laplace transform, and that may not be trivial in all cases, okay? So let's also express y of s. Now y of s is equal to c times x of s plus d times u of s. Now I have obtained x of s, so I will just put it in. So I have c times si minus a inverse b plus d times u of s. So I have taken it into u of s parentheses. Now what is my transfer function? Let's call it t of s. is defined as obviously the ratio of the output to the input in the Laplace domain. And what is that? Well, that is nothing but C times Si minus A inverse B plus D. Okay, so that is my transfer function from the state space system expression. Okay, now let me try to apply that to our example. Okay, back to our example. What is our example? Well, our example is here, where we have obtained these this A matrix, this B matrix, and this C matrix, and this D matrix, which is 0 in this case. Okay. Now, so let's first calculate. Okay. Let me switch to blue again. So Si minus A inverse is the first thing that I'm going to try to calculate. What is Si minus A? Si, well, Si is something like this. S0, 0, S. Okay, it is the identity matrix multiplied by S. So all the ones become S. The remaining parts are equal to 0. So this matrix is the inverse of S minus 1 over C, 1 over L, and S plus, because we had minus R over L, S plus R over L inverse. And that is equal to, we know that it's going to be equal to 1 over the determinant of, let's call this matrix M. Okay, so that's going to be the determinant of M times the adjoint. If you remember matrix inverse, I need to calculate the adjoint of M. And that's going to be equal to, what is the determinant of M? So determinant of M is basically these two entries multiplied minus the other diagonal entries multiplied. So that's going to be S times S plus R over L minus minus 1 over LC. So that's going to be equal to S squared plus R over L S plus 1 over LC. That's the determinant. Okay, so this is equal to 1 over this polynomial, S squared plus R over LS plus 1 over LC. Okay. And the adjoint of M is, let me put a reminder here. Reminder, adjoint of A, B, C, D is equal to D minus B minus C and A. Okay, so that's gonna help us write down the adjoint of A. That's gonna be equal to S plus R over L, 1 over C, minus 1 over L, and S. Okay. So our transfer function, which is equal to B times Si minus A inverse. So what is B? B was equal to 1 and 0. And then let me call this as a shortcut Q of S. In fact, this is known as our characteristic equation. So 1 over Q of S times S plus R over L, 1 over C, minus 1 over L, S, and times, sorry, this was C, right? This is C, and SI minus A inverse, SI minus A inverse here, and this is our B matrix, which is 0 and 1 over L. And we know that we have D is equal to 0, so that doesn't come into play. So if you do these two multiplications, first these two matrices, and then a multiplication with C, so your transfer function will come out to be 1 over LC. It's going to be a scalar because, you know, this is a 1 by 2, this is 2 by 2, this is 2 by 1. So T of S will turn out to be a scalar quantity. And that's going to have in the denominator our characteristic equation. S plus 1 over LC. So it's a second order transfer function as expected. Okay. So that is how we can derive a transfer function for a given state space representation. Let me make an important note here. Okay, so obviously you will, in order to be able to deal with the state space representation, you will need to review some of your basic algebra skills, like, you know, basic linear algebra, determinants, inverse, at least for 2 by 2 and 3 by 3 matrices. Also, I would recommend Gauss-Jordan elimination, because that can be also used in order to take matrix inverses. Okay, essentially you need to know the determinant and inverse of 2 by 2 and 3 by 3 matrices. You should be comfortable with, at least for the purposes of this course. Okay. Now let's take a look at the second question. Okay. Basically, how can we arrive at state space representation from a transfer function representation? Okay. Now, a first note is about the uniqueness of this. Okay. Is such a state space representation unique for a given transfer function? And the answer is no. Okay, and I would like to prove it to you. This proof, in fact, in your later courses you will see you know, this kind of transformation used for other more advanced proofs as well. Okay, so so our note is that A, B, C. Let us forget about D for a while. Okay, I will show how D can be obtained later on. Okay, for now, let us assume D to be equal to 0, and we claim is that ABC matrices are not unique for a given transfer function. And I will try to prove it to you, okay? And the proof goes by assuming another state space representation and showing that this alternative state space representation in fact has or may have the same transfer function. Okay, so let us define some new states based on the original states. Okay, and let us define these states as phi and let it to be equal to t to the power minus 1 x. Okay, where t is an n by n invertible matrix. This is known as a transformation of the state because we are multiplying the existing states by a matrix that is invertible to obtain new states. Note that because t is invertible, what I am effectively saying is that x is equal to t times phi. Okay, so both of these equations are identical. Okay, so now phi is the new state, and let us try to write down our equations in terms of these new states. Okay, so what is the derivative of the new state? The derivative of the new state is the derivative of the old state, but is multiplied by t to the power minus 1. So because I know what x dot is, I can simply write it down here. X dot is equal to ax plus bu. Okay, and therefore what I have here is that I have t to the power minus 1 ax plus t to the power minus 1 bu. But I also know that x is equal to t times phi, so I will have t to the power minus 1 a t phi plus t to the power minus 1 b u is the derivative of the new state. Okay, now if you take a look at this, you basically see a new state space system where this combined matrix, we can call it our A prime matrix, and this combined matrix we can call it the B prime matrix, and therefore this becomes phi dot is equal to A prime dot phi plus B prime dot u. What about the output equation? Let's also write that down. Now y is equal to c times x. Okay. Now I know that x is equal to t times phi, so this is ct times phi. Okay. And that ct becomes our new C matrix. So let's call this C prime, and we have y is equal to C prime times phi, phi being a vector. Okay. So what is this? This is another equally valid state space representation. So we have shown that under a transformation of this type given here, we can actually obtain a new state space representation, but we haven't yet answered our original question. Is that what I'm going to do now is to show that these two state space representations have exactly the same transfer function. Okay, now show that let's say this is okay. Show that the two representations have the same transfer function. And that's going to complete our proof. Okay? So what I'm going to do now is to simply compute the transfer function for this new system. So let's call it T prime of S. That's going to be equal to C prime S I minus A prime inverse B prime. Okay, so let's put in all the definitions. C prime is equal to CT. Si minus, I have t to the power minus 1 at for A prime inverse. And what is B prime? Is that it is equal to t to the power minus 1 times B is my B prime. Okay. Now, in order to simplify this, I also need to use a couple of identities. First, I need to write down that the identity matrix, in fact, is equal to t to the power minus 1 times t. So a matrix multiplied by its inverse gives us the identity matrix. And I also need to use a result from linear algebra, is that if I take the inverse of a multiplication of matrices, what I have is in fact the inverses of those matrices, but in the reverse order. Okay. So here I'm going to write this as t minus 1t. So I will have ct s t minus 1. Okay, s t minus 1 t minus 1 a t inverse t minus 1 b. Okay, so let me take this into a parenthesis, ct st let me do this. Take this into t minus 1 parenthesis over here, so that I will have si minus a, and on this side a multiplication by t and inverse t minus 1b. Now I'm taking the inverse of 3 matrices inside, so that's going to be t minus 1 minus 1, the first will be the inverse of this, so that's going to be t minus 1, the inverse of the middle matrix, and the inverse of this, which is going to be t. Okay, so what we have here is that ct, and in the inside I will have t minus 1, si minus a inverse t minus 1 b. And if I open up the parentheses, what I have is ct t minus 1 si minus a inverse t and t minus 1 times b. Now these result in identity matrices, and that gives us c si minus a inverse times b, okay, which is equal to our original transfer function. Okay, so t prime of s is equal to t of s. These are the same. Okay, so that is that completes the proof. So what is the result? Two different state space representations have exactly the same the same transfer function. In fact, since we can select T as long as it is an invertible and square matrix, in fact, we have infinitely many. Okay, so since we can choose T, in fact, not only two different state space representations, but infinitely many state space representations have exactly the same transfer function. Okay, so that completes the first part of our statement, which means we haven't yet answered how we can obtain a state space representation for a given transfer function, but at least we have shown that such a state space representation is not unique. There may be infinitely many such representations. Okay. Okay. Now, let us first look at, first consider how we can obtain the D matrix. Remember, we assume D to be equal to 0. Okay. In fact, I will show you how we can obtain D uniquely. Okay. And we will move on by assuming D to be 0, because you can always obtain D in this manner. Okay. So let me give you an example. Let's say that our transfer function, and I'm going to write this down as g of s in this case, is equal to s plus 1 over s plus 2. The interesting thing about this is that the numerator polynomial is of the same order as the denominator polynomial. Okay. Now, let us see what that means. Now, let us make a long division. Divide the numerator by the denominator. So that means I'm going to divide s plus 1 by s plus 2. Okay, so let's say these are the same order, so I will have s plus 2. Let's subtract, s's are gone, so I have minus 1 here. So what I am effectively saying is that g of s is equal to 1 minus 1 over s plus 2. Now the numerator is of degree 1 less than the numerator, and we have here another term. Okay. Now you can convince yourself that this term over here is nothing but D. Okay. So the D matrix is equal to this result and is unique. Okay. So we don't have and we won't have infinitely many choices for D. D will be uniquely defined by this division. Okay. Now, apart from this D, meaning D is equal to 0 assumed, we will assume that degree of the numerator will be smaller than the degree of the denominator for the rest of our discussion. So if D is equal to 0, we will have this assumption satisfied, and in fact, therefore, for the rest of our discussion, we will limit ourselves to the general form of a transfer function where I will have the numerator being 1 degree less than the denominator. So I will have s to the power n plus a1 s to the n minus 1 plus an. So numerator polynomial is s to the power n minus 1, and the denominator polynomial is s to the power n. Okay. Will be assumed for the remainder of our discussion. So I'm quite tired. I'm gonna break the video at this point, and we will continue in the next video. Okay.